Okay, so our final speaker for today is Professor Phuan Ong from Princeton, and he's going to be talking about the chiral anomaly in sodium-free bismuth.
Okay, thanks, Monica. All right, so I'm going to talk about experiments which I'll try to convince you provides evidence for the chiral anomaly in sodium-free bismuth. So this is sort of the continuation, I guess, of Ed Witten's talk this morning, but hugging close the rail axis. So I'll try to make connections between these calculations of quantum field theory to things that we can actually hold in our hand. All right, so let me first acknowledge my co-workers. These are students and postdocs from my group, Xiong, Liang, Hirschberger, and postdocs and students from Carver's group, Kush Waha, Jason Crism. So I'm going to start by taking a sort of easy intro into how we got into this area. Of course, we're inspired by the many theory papers from Charlie Kane and others. And then I'll talk about the band structure of sodium-free bismuth, sort of the road that led to this gap closing phenomenon to realization of sodium-free bismuth. And then I'll give a very short intro to chiral anomaly because Ed has given such a beautiful intro. And then I'll talk about the experiment, the observation of charge pumping, which we interpret as a very narrow current plume that can be steered by the magnetic field. And of course, we acknowledge the folks who pay for the liquid helium, the biggest expense in our budget. So the whole area of topological insulators and extensions has led to a cornucopia of many materials now, and it keeps spreading, and that's great. So let me just briefly give a roadmap. So, it started with these Z2 time reversal invariant systems, mostly based on bismuth that we heard from Hassan and Charlie King. And in parallel with these quantum spin Hall systems that Amir just discussed a few minutes ago. But now it's sort of spread. So let me just quickly walk you through this. The topological crystalline insulators, latin telluride and so on, that you heard about from Didier. Even in the insulating materials, pyrochlore, spin liquid systems, again, pyrochlore based on the iridate, so the samarium hexaboride. These are perhaps strongly correlated versions of the bismuth systems. Related to the layered materials, the moly disulfide, tungsten telluride. So the talk today will be on the topological Dirac semimetals, and this will have relation to the wild metals that perhaps Zahid will talk about later. The common feature, which I've drawn as a viral particle, is this notion of Berry phase and Berry curvature. And a lot of these phenomena, especially as they relate to transport, are basically informed by the existence and presence of the Berry curvature. Okay, a quick indication of how we thought about this initially. So we were following the work of Murakami, who quite a while ago, starting in 2007, started thinking about this old problem of how gaps close in three-dimensional bulk materials. So this was studied a lot by semiconductor physicists, but with the advent of the topological ideas, this whole field is undergoing very rapid changes. Okay, so when you try to force two bands to close, a gap to close rather, right? So you can think of several scenarios. The three would be the following. It could be anti-crossing because bands just do not like to close, and so they could try to avoid each other. So that would lead to anti-crossing. Nothing interesting happens. The two interesting cases are when you have a line node, where you have a node of zero energy encircling the extrema. Actually, there are very few examples, but it's again an area that is rapidly evolving. More specific to our interest, the bands could actually close only at discrete nodes. And later on I'll show that the modern understanding is that actually when that happens, you start with two gap areas, right? Then they close to form protected nodes. And if you extend this parameter some more, each node will split into two wild nodes, and then the two wild nodes will travel through the Brillouin zone, and they will close somewhere else to form Dirac nodes, and eventually open up again. Right? So that's the interesting scenario. Now, many people, of course, have thought about this, and I'm showing only a few of the papers here. I think starting in 2012, Keynes' group started to think of this, how might you realize protected Dirac nodes in a three-dimensional material. And they postulated that perhaps if you had time reversal symmetry and inversion symmetry, the nodes will be protected if they are pinned to the corners of the Brillouin zone. And they even came up with compounds that might do that. And I showed this paper, this very famous paper, to Bob Carver, and he immediately dismissed it as a physicist's dream. Because it turns out that these compounds are not stable, not chemically stable. So today we would call this, following Charlie's terminology, a non-symmorphic case, which means that the system has glide planes and screw axes. Now the other case, which was realized by many groups, Bernard, for example, was that if you now introduce point group symmetry, so now you have three symmetries protecting the nodes, you don't need to pin the nodes at the corners of the Brillouin zone. They will be stable anywhere along the symmetry axis. So for example, I'm drawing two point group symmetries, C3 and C4, so the symmetry axis is coming up towards you, right? So the node can sit anywhere on that symmetry axis and still enjoy protection. So this, for experimentalists, was a crucial observation, and that led to the discoveries that these two materials were actually suitable candidates. That was identified by the IOP group, Wang, Shita, and so on. Okay, so we're going to talk about this second class, which is now called Topological Direction. Okay, the paper that I've identified here reports the detailed LDA calculations. What I'm going to do is to simplify this considerably and basically boil it down to the essential points for the experiment. Right? So, and you see the similarities with the discussion that Ed Witten talked about this morning. All right, so you have 8 bands, as Amir indicated, if you focus on the two bands from the 3s and the 6p from the bismuth. But there are 2 atoms per unit cell, so you have 16 bands, right? Counting spins as well, right? So fortunately, only 4 of them are relevant. The 4 are the S band with a spin plus or minus 1/2, and the P band with the 3/2. All other bands are pretty remote from this. Now, spin-orbit coupling will pull the S band down, as Amir explained, and that leads to a crossing of the bands along the z-axis. So this is the node that is protected because the sample has crystalline C3 symmetry above the z-axis. And therefore, that's where you would expect to see the Dirac node. So here's a sketch of what the Dirac dispersion looks like. Okay, all right. So here are the two compounds, again, to repeat the point. So if it's C3, it's sodium 3 bismuth. If it's C4, it's cadmium arsenide. This turned out to be a harder system to work with, even though it's stable. Right? The reason is the bands are anisotropic for reasons that are not quite clear. So we've done a lot of transport on these as well. So these are actually harder to interpret. But nonetheless, the Dirac nodes are similar, and they give rise to two Fermi surface pockets along the z-axis. Sodium 3 bismuth is a gift. Even though it's very hard to handle, it spontaneously ignites. But it doesn't ignite. It just stands there and turns into white powder after 30 seconds. So you can imagine the difficulty of making experiments on this material. But nonetheless, it is sufficiently simple that, as you'll see, you get to see a lot of phenomena that will be of interest. The band structure is hexagonal. The crystal structure is hexagonal. There are two planes, and they are staggered, and there are two inequivalent sodium sites. But all these details are irrelevant to the band structure. The only thing to note is that the crossings occur along the z-axis. So very quickly, after the IOP group published the band structure, the RPES measurements were done. Here I'm showing the data of Yulin Chen. And you can see the Dirac node, the pinch-off point here, that's the node. And then a little bit here, you can see the Dirac cone opening up, right? So it depends on the doping of the material. Now, the difficulty of making the Fermi energy sit right at the node comes from sodium vacancies. These crystals are difficult to grow, so there'll be some number of vacancies. And we generally see the Fermi energy significantly higher than the node, right? So you will see the numbers in a little bit. Now, if you look at the simplified version of the Hamiltonian, so basically I'm taking the IOP Hamiltonian and moving very close to one of the nodes. So to leading order, you find that all the terms vanish, and what this 4x4 Hamiltonian boils down to are two wild nodes, right? So this is now written in the representation of the S and P states with the spin 1/2 and spin 3/2. So again, you see that the reason why the node is protected is because not only do S and P belong to different irreducible representations, the columns of the character table, so to speak, are also different. So no matrix element can be formed between any of these states. Now, if you take these two by two blocks, let me just take one of them, call it H1. You find that if you write it in terms of the Pauli orbital matrices, this is the form, right? Now, this can also be written in this matrix form that Ed talked about this morning. I think he used the notation AIJ. So if you look at this, you easily see that the velocity matrix is diagonal, but it has a determinant of -1. So this is how you determine the chirality. So the chirality of the upper block is -1, that of the lower block is +1. So even in zero magnetic field, the protected Dirac node is already resolved into two wild nodes, which is depicted here. The yellow cone is sitting right on top of the gray one, but in a magnetic field, they presumably split. So we got really interested in this material, and Bob Carver's group started to grow them. And this is really tough because it turns out that this material grows in two forms. One is sodium 3 bismuth, that's what we want, right? But the other one is sodium bismuth 1,1. And that material is a superconductor. So when we first studied it, we not only thought we had a topological Dirac semi-metal, it goes superconducting as well. You know, it's like, you know, there's nothing more than you could want, right? But it turned out to be a completely different phase. And so they had to go back and look at the phase diagram carefully and eventually extracted the true phase, which they call 2 here, right? But you can see that it grows as beautiful hexagonal platelets. So these are truly nice macroscopic crystals. June developed the technology to remove the crystals in an argon glove box, immediately cap it in oil so that it never sees New Jersey air. Sure to kill it. And then with it buried in oil, he cools it down right away. So doing that, you can actually cycle the sample several times over the course of a week before it dies. So, okay, this first set is actually not quite appropriate because, as already emphasized by Ed, you really need to get very close to the node, right? In fact, the initial batch had the Fermi energy 400 millivolts above the node. This looks very large. But remember, the velocity of the Dirac cone is very high, so that it doesn't take very much to push the Fermi energy way above this maximum here, which is called the Lifshitz point. Anyway, I'm going to show this because it's still interesting. It's telling you that there's more physics going on here than merely chiral anomaly. And this part is still a mystery, but I'll just show you what it's doing. Right? So the resistivity profile looks metallic, nothing interesting about it versus temperature. But when you look at the magnetoresistance, you see this spectacular linear field, H linear magnetoresistance. And this is a puzzle. It shouldn't be there. It's enormous, and you know, it varies with angle and so on. No trace of the chiral anomaly in this set of crystals. Still on this material, this linear MR is seen here. I'm showing 7 samples, some taken to fields of 30 Tesla or more. They have very unconventional transport properties. Hall angle is flat versus a field, where it has this step. And the conductivity matrices are all highly anomalous. So there's still a mystery why you have positive linear MR to begin with, which implies all these strange properties. The mean free path is very large, mobility is very high, and you can see beautiful quantum oscillations that allow us to determine the effective mass and the anisotropy. The anisotropy of the Fermi surface is not significant, but nonetheless, all these measurements did not really teach us much about the chiral anomaly. So to move on, let me first see. All right, so now I'm going to talk about a new generation of samples where we are seeing things that are very different and I think indicative of the anomaly we're talking about. So let me first step back a little bit and remind you of the history. So the chiral anomaly was first found by folks doing pion physics. So the lifetime, oh, this is wrong. Let me switch to this. If you look at the decay of pions, you find that neutral pions decay 300 million times faster than their charged cousins. They all belong to the same isotriplet, so it's a bit isospin triplet, so it's a bit mysterious. Then Adler, Bell, and Jakiv found that it's because they couple to electrodynamics. Well,